So, good afternoon and welcome to, I think this is lecture 3. I believe you have been taking time to go through the previous lecture notes and videos. So, we are making steady progress in trying to understand machine learning for computational linguistics. So let me share my screen so that we can quickly review. Um, but before we do that, are there matters arising? Are there matters arising? Questions, comments, observations that you want us to talk about? In the last lecture, we discuss the foundations of machine learning, and we try to define machine learning. We emphasize the fact that the heart of machine learning is to find patterns in the data and use the machine learning algorithms to predict uh, new observations. So you need uh, high quality data, and you also need a large amount of data. So we emphasize that there are three key parts or components of machine learning: the features, uh, the labels, and then the model. Then we discuss the three types of the machine learning uh, categories. The supervised, and we took time to explain that, the unsupervised, and of course the reinforcement learning. And I emphasize that our focus will be more on, just a minute. Sorry for that break. So I mentioned the three categories or three types of machine learning that we have: the supervised, the unsupervised, and then of course the reinforcement. And I emphasize that most of our discussions in this class we focus more on the supervised approach or techniques. And some of those techniques were also mentioned. And then we close the the lecture, at least from my side, on the basic concepts, the important concepts in machine learning. Um, what we mean by uh, training data, what we mean by test data, what we mean by overfitting, underfitting, features, labels, and of course, accuracy, uh, which is a measure of the performance of your machine learning uh, classification algorithm. So we discussed all of that, and we took examples for purpose of illustration, and we listed common algorithms in natural language processing. Some of them will begin to implement today, particularly the naive Bayes. There are also logistic regression, decision trees, neural networks, and so on. And we review 7 steps for um, we review 7 steps in typical machine learning projects, uh, beginning from how we define the problem, how we collect data, how we prepare the data, uh, how we choose our model, pick the right algorithm, how we train the model and test the model, and then if the performance is not um, good enough, then you need to improve before you deploy. And improving the model requires that you look at the data. Maybe you need more data. Maybe you need to consider other, you know, algorithms. So you need to, you may also need to, uh, change some of the parameters. You will learn about that as we continue. So that summarizes uh, the last lecture. I believe uh, you have taken time to revise on your own. Make sure you do that as frequently as possible. So today, I will um, take you through few concepts, and then we will also use data to reinforce the topic or the discussion. Then uh, you, I will hand you over to my colleagues as usual to review and also consolidate on whatever we are able to cover in this lecture. Um, but if there are questions now that I need to quickly address, you can always interject and let me know. So the topic for today is, of course, probability and Bayesian inference. I believe you we've been talking about not in this class. So most of you uh, probably will be. I don't know if you are hearing the word probability for the first time, but it's a common word which simply measures uncertainty. So in life, many things are uncertain. Um, so if right now, if I ask you whether it will rain tomorrow, I'm sure you might say yes, you might say no, but obviously you are not sure. Nobody is sure. Uh, so uncertainty, is um, a major concern, in human affairs, and probability quantifies the uncertainty. So only few things can be said with 100% assurance. You know, um, I don't know. Is anybody here able to tell me something that you know is 100% certain? Is anybody responding? Chiamaka,
Sir,
is there anything you know that is certain?
that is certain.
Yes.
Um,
You are in the you are in Bodija market, I suppose.
yes, sir. Yes, I am.
So it's okay, mute yourself.
Okay, sir.
But let me go to Vivian. Vivian, are you there? Vivian. Vivian too is not there. Maybe I'll be forcing. Okay,
Okay, sir.
internet. Yeah. Mercy, are you talking?
So I wanted to say that if I'm not certain about any other thing, I am certain of the fact that I am,
A
that I
female.
exist.
Yeah, that you are a female, isn't it?
Yes. Because I wanted to say I'm certain of the fact that I know, but some people will say, how are you sure that you know? How are you sure that you know the things you know? Those kind of things, I don't know. But I know that I'm existing, that I'm sure of.
Okay, that's a good one. But you also know that if if you if you toss a coin, let's perform any experiment. Um, you know, uh, are you so sure? Okay, Vivian, I'm coming to you. Are you so sure of what will be the outcome of that experiment? Uh, Certainly, no. Even though life is an experiment, and even though you know you are living, you are alive, but what is uncertain is when one will die, how one will die, where one will die. Or do you know all of that?
No, sir.
So, maybe Mercy knows.
No, I don't know, sir.
Uh-huh. So those are the uncertainties. We know you are alive today. I know I'm alive today. But do I know what will happen in the next moment? Do I know how it will happen? So there are many really issues like that. Uh, just as it is uh, you know, in life, we can also bring the perspective to language. Vivian, I know itching to say something now.
No, no, sir. I mistakenly pressed the leave button when I was trying to answer the last time. So I was
Okay.
going to say that it's certain that I'm putting on a clothes right now, and it's also certain that and it's also certain that I'm hungry. So
Oh,
I think those one could pass.
yeah, but okay. You are also not sure the clothes you will wear tomorrow. I know it's not only one cloth that you have, except you have determined. You may also not know, even though you know you are hungry now, you are not sure uh, uh, what meal you are likely to take, where you likely take the meal. So there are so many uncertainties, and that's what probability helps to measure. So if you are certain, then the probability is one. If you are uncertain, then the probability uh, uh, is between 0 and 1. Um, but the closer to 1, then the higher the likelihood of the event occurring. When it is 0, then it's an impossible event, or it means it's not possible. So uh, we will talk more about that. So here we are simply saying that how then do we bring up what is the connection between probability and language? Uh, with the yes, Vivian.
Sir, please, you're not sharing your screen, or is it my network? I can't see your screen.
Oh, nobody told me. Sorry, sorry. Okay, can you see my screen now?
Yes, sir.
Yes, sir.
Okay, some people just kept quiet without asking question.
We thought you were still just explaining stuff.
Yeah, I'm speaking to uh, the lecture manual. So I said that there is a connection between language and probability, and we've been using several examples when it comes to uh, language, and in particular, uh, we've been using the example of the next word that will come when you are forming your sentence, or uh, in the case of email messages, you know, you are not sure whether an email is a spam email or a legitimate email. So machine learning models uh, use probability to make predictions, to make decisions, to be able to classify whether an email is a spam or not a spam, and is used in other uh, other aspect of natural language processing. So when you hear something like there is a 90% chance that an email, for instance, is a spam, what does that connote? Um, Yes. What does that connote? If you hear, that there is a 90% chance that an email is spam.
That means it is actually spam. We agree.
Are you
90%.
90% doesn't make it certain. Um, if it's 100%, that would be certain. But when you see 90%, which is if in fraction 0.9, it's not certain, but is the chance is very high. Uh, so which means you still have 10% chance that it is not spam. So probability lies is a number between 0 and 1, or if you put it differently, between 0% and 100%. So if the value is close to 0, it means it's a real event, that the event is not likely to occur. If it's very close to 1, or in terms of percentage, is close to 100, then it tells us that it's highly likely to happen. So if I tell you there is a 90% chance that an email is spam, it means it's highly, most likely the email is spam. But it doesn't mean it is spam, because you still have 10% chance that it is not spam. But so that percentage is a measure, which is what we call the probability. So in daily language, you can hear the word the chance is high, is most likely, and so on like that, but without putting numbers, without putting quantities. That is not probability. Probability will have to be expressed in number, and that number is interpreted based on how close it where how where it falls between the range of 0 and 1. So if the probability is 0, it simply means the event cannot happen. And if it is 1, then it means it will certainly happen. And we'll have a simple example here. As much as possible, I try not to be too technical because of just a minute. Sorry. Sorry, I'm back. So I was saying that I want to, as much as possible, make it very simple for us. So the point we are making is that probability is usually a value between 0 and 1. And so it could be, it's not, it's never greater than, it's never greater than 1, and it's never less than 0. So put that in mind. And whenever it is, for instance, if I say probability of A is equals to 0, it means this event A cannot occur. That this event, is impossible. So it means impossible. When it is 1, let's say I say probability of B is equals to 1, then it means this event B is certain. So, so probability then is between 0 and 1. It could be 0, it could be 1. But if it's closer to 1, then it shows is most likely. If it's closer to 0, it shows is no, no, very rare. No, it shows is very rare, not likely to happen. So that's very important for you to take note. And then here we talk about the experiment, for instance, of tossing a coin. So it's usually a common example when we teach probability. You have a coin, and the coin has two sides, head or tail. So when you toss the coin, these are possible outcomes. So we call this one possible outcomes. So if the coin is fair, which means it's not loaded, then you can talk of probability of a head occurring. So by definition, you have to look at the possible outcomes and then look at how many of these possible outcomes are favorable. So the probability of a head will be the number of heads in that possible outcomes over the number of possible outcomes. That's how probability is defined. And since we have in that possible outcomes only one head is favorable, so then it means you have one out of how many possible outcomes? Out of 2. So this is 0.5, or if you like, you can say 50% chance of head appearing. So always remember, if in this class you have 4 girls or 4 females and you have 6 males, then if I'm interested in the probability of male, then I will say how many males are in the class. I have 6. Then those are the favorable ones. How many students are in the class? That's 10. So I have 10. So this now becomes 0.6, or if you like, you say 60%. Vivian, is that clear?
Very
Let's
clear,
see.
sir.
It's clear, sir.
Okay. Olowu, you are still in the...
It's clear, sir.
Okay. So if it is clear, then heritage, what will be the probability of female?
So the probability of female.
Yes,
60%. Ah, I'm sorry, 40%.
40%, which is 4 over 10, right?
4. Yes, sir.
0.4.
4.
0.4. So this is how we, we measure probability. So probability is number of favorable outcomes over number of possible outcomes. So that helps you to always know how to measure uncertainty. That helps you to measure uncertainty. So we are still coming to do more of that. Now, another concept that is very important is the concept of conditional probability. The concept of conditional probability. So, and so conditional probability. Like I said the other time, if you have 4 females and you have 6 males in the class, and you are going to pick, you want to pick 2 students. So the first time you pick, you can pick a female, you can pick a male. So like we computed the other time, then the probability of female, so probability of female will be equals to 4 over 10. Then probability of male will be equals to 6 over 10. Of course, you said this is 0.4. This is 0.6. Now, if you go to the second stage, after picking the female, in the second stage, you could also pick female or a male. If you pick male in the first, you could also pick female in the second or male in the second. now there will be an issue. So we can talk about probability of female in the second, female in the second, given female in the first. So if you pick female in the first,
Now we can't see what you have written.
you can't see what I've written here. Okay, let me go.
Yes.
Okay, let me open a new page. So what I'm saying is that in the class, you have four females, you have 6 male. So, and you want to pick 2 students, one after the other. So you are picking 2 students. So if this is the first selection, then you could pick either a female or a male. And I said the probability of female here will be 4 out of 10. And then the probability of male here will be 6 out of 10. Now we are going to the second selection. Second selection. In the second selection, you could also have this scenario if female was picked in the first. So you could also have female or male. Also, if male was picked in the first, you could also have you could also have female or male. So I want to explain conditional probability because what will happen in the second will depend on what happened in the first. So that's what I'm writing when I say probability of this one, female in the second, given female in the first, which is referring to what happened here. That probability, you will agree with me. Who is going to tell me? Remember, you have picked one female in the first. So how many females are left? Vivian, if you have picked female in the first, how many are left? 3.
3, sir. Yeah.
Good. So how many students are left?
9.
9. So what
Yeah.
will now be this probability?
3 over 9.
3 over 9.
Yes, sir.
This probability is what we call conditional probability because it's conditioned on what happened in the first selection. So I want somebody now to tell me the probability, this one, the probability of male in the second, given female in the first. Who is telling me? Who is telling me? Olasoji?
Okay, sir.
Okay, yes, Olasoji, yes.
given second, okay, given male in the second, or probability of male in the second, given female in first.
Yes.
Okay, if I understand, sir, that would mean that a male has been picked in the first.
How many males are left after I pick female in the first?
Okay, we still have 6 males left.
We still have 6 males.
Yes,
But
sir.
how many students are left?
9.
9. So what is the answer now?
So the probability of male now will be 6/9.
6/9. Excellent. Right? So this is the chance you have of picking. Yes, Vivian.
Sir, you said probability of male in the second, given female in the first. The
Yes.
female in the first there is forced, they are forced. So I want to understand the second part, given female in the first. Because the female in the first will no longer be, will be 4, and the male in the second will be 5. So this thing I don't really get it.
Okay. Here, we are looking at probability of male in the second, given that female was chosen in the first. Right? Vivian, you have to respond.
Oh, yes, sir. Okay, given a female was chosen from the total of the number of students. Oh, yeah,
So you
okay.
have chosen a student. So the total number of students remaining is 9. So, but out of these 9, how many of them are males? So 6 are still males because you have not chosen a male. Vivian.
Yes, sir. Yes, sir. I get it now. So it's given that a female has been chosen. I was trying to understand the interpretation of the M2 over F first. So I get it now.
Okay, good. I'm happy. So you can complete the rest. I just want you to have idea of what conditional probability is all about. So when we talk about conditional probability, is the chance that something happens given that something else has already happened. So how do we write it? This is the way we write it. So whenever we write probability of A given B, we are simply saying probability of A given that B has happened, as we are trying to show here, that probability of male given that, so female event has no selection has happened. So we are interested in what is the probability of male, right? So the concept of conditional probability is simply measuring the chance of an event occurring, given that an event has occurred. So, example, probability that an email is spam, given that it contains the word free. Let's look at this data very quickly. This is somehow a very simple data. Now, here you have ID, which represents the number or the serial number of the message received. So this is the message. And here you are looking at whether in that message the word win appears there. Here you are looking at the word meeting, whether it appears in the message. And here we talk about label in the last class. So the label tells the category where the message belongs. So here in the first message says, win a free iPhone is what is contained in the message. That's the message. So win is there. So yes, but the word meeting is not there. And we suspect any message that contains the word win as having spam. So this word is classified as spam. This one is regarded as not spam. Congratulations, you win cash. That has the word win. So you have one. But from this simple data, you will see later how we compute both while we compute probability, that is the likelihood that a message will be classified as a spam, and the likelihood that the message will be classified as not spam. This is to help you to see the application of probability, conditional probability, in linguistics, in the study of language. So we are still coming back to this, but for now, understand what conditional probability means, and how the notation for the expression for conditional probability. Now, another very important concept before we look at the application, and then leave you with my colleagues to further make the discussion clearer. Now, Bayes' theorem is a very popular theorem, and is widely, it has a very extensive applications in natural language processing. And it's just a way to update probabilities, as new information, is received. So we talk of updating our knowledge, talk of incorporating what we believe, with evidence. So our belief is incorporated into the data that we gather. So if you have this is total probability, for instance, and you have this event, this is event A, this is event B. So this is what is common to the two. So This is what we call the intersection of event A and B. So you can regard this place as the part of B, this place as the part of B that is in A, as well as regard it as the part of A that is in B. So this place is called A intersection B. So that is the way, that is what we call the Venn diagram. I'm sure most of you are very much familiar with that. How many of you are familiar with that? Type yes if you are familiar with that. So nobody has typed yes. Mercy, that's good. So that's good. So we can talk about, yeah. Oh, almost everybody is familiar with that. So we can define that probability of A intersection B, this particular place, to be probability of A times probability of B given A. That is, this particular place is the probability of A multiplied by the part of B that is in A, if that will help you to understand. This same expression could be written as probability of B times probability of A given B. Again, I could say this is the probability of B multiplied by the part of A that is in B. So again, you have that. And that leads us to very important formula, which is what we then call the Bayes. Now, since these two quantities are supposed to be the same, this is probability of A intersection B, probability of A intersection B. So it's possible for me to equate the two as probability of A times probability of B given A is equals to this one also, which I can call probability of B times probability of A given B. So I can write it that way. So if I'm now interested in this, let's say I'm now interested in this probability. So all I need to do is to divide both sides by probability of B. I don't know if it's not becoming clumsy now. So if I divide both sides by probability of B, then on this side, I will have probability of B On this side, I will have probability of B. Of course, this one will cancel this. So I am left with probability of A given B to be equals to probability of A times probability of B given A divided by probability of B. For purpose of for clarity, so which means I can. Yes, Vivian.
Sir, it's becoming too technical. Please, like,
Who
can you
te-
help us can you help me slow down a bit? Let me not generate. It's becoming too technical. So I got lost where you say you divide both sides, whether it's by A or B, and one is canceling one. What is canceling what
Okay,
exactly?
okay. Sorry, let me go back. So I'm going back. So let me go back. Maybe so that expression, if you recall, so I'm going to rewrite that expression, this expression, and this expression, because these two are the same. If I say this is equals to this and I say this is equals to this, then these two are the same. Do you agree with that, Vivian?
Yes, sir.
So to make it clearer, let me just clean this part so that I don't have to open another page. So,
While you are cleaning that,
eh?
this slash, is it a divide sign or is that what you have been calling giving that?
Yes, that's what we call giving that. So it's the
Giving that.
notation, it's a slash, but it stands for giving that. Is that okay, Heritage?
Yes, sir.
So, which means I'm trying now to equate this and this together. And then, so I can write probability of B, times 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 probability of A given B to be equals to probability of A times probability of B given A. So what I want, so I've equated this to this. So what I want now is this probability. I want this one. So if you have, for purpose of, if you have AB equals to KM, then if I want only B, then I will divide both sides by A. So I will have AB over A equals to Km over A. So I'm left with B, so I get the B which I want to be Km over A. So if I apply that principle here, I take this as my A, I take this as my B, I take this as my K, I take this as my M. So, which means I can now have, let me do some clean. So, the eraser is not clean. So I can now have, sorry, okay. So my pen is misbehaving. That's why you're good. How do I do it now? Okay, so I can now have probability of A given B to be equals to everything here, that is probability of A times probability of B given A over probability of B. Okay, let me open another page to make it clearer. So I have probability of B times probability of A given B to be equals to probability of A times probability of B given A. So I want probability of A given B as the subject. So I have to divide everything by probability of B. So which means I have probability of A times probability of B given A divided by probability of B. So this is where we are going. If you go back to where we actually, this expression is what we call the Bayes theorem. Is the formula for Bayes theorem. But again, if you go back to the expression that I have here, look at probability of the intersection, which is probability of A times probability of B given A, then this. Now look at what we have here. You will see that what is in the numerator here is nothing but probability of A intersection B over probability of B. Which means when you have this Venn diagram, and this is A, this is B, right? And this is the intersection. Then if you are interested in the probability of A given B, A given B, then you are looking for this part of A that is in B. That's what this is saying. This part of A that is in B. So it is the expansion that gives you this. So this one is what we call this probability of B, which is the denominator, is what we call total probability. It's what we call total probability. So this expression, as I've said, is the Bayes theorem. So this is what is given here. The Bayes theorem says the probability of A given B is the probability of B given A times probability of A. Of course, what you see here is that I actually started with probability of A, but it doesn't matter because you are actually multiplying. Whether you say A times B is the same thing as B times A. So that expression is what is defined there. And we are going to use it. We have a lot to say about it, but time is not enough. I think that will, my colleagues will further discuss that. So let's now go to the application that I have for you. Now look at this data. Look at this data. So we will quickly take this data now to the R environment. One, we want to how we use the Bayes classifier, which is where we are going now. We have the naive Bayes classifier to be able to say, okay, if I get another message, will I be able to predict whether that message is a spam or not? So that's what the Bayes classifier will help us to do. So it will help us now to look at a message that is coming, a new message, and then be able to use probability to say, yeah, this message is a spam. Don't act on it or delete it. Or this message is not a spam. So one technique is for doing that classification is the naive Bayes classifier. So there are other techniques which we will discuss subsequently. But when it comes to predicting whether an email is a spam or not an spam, or not spam, the Bayes classifier comes in so handy. So in this discussion, it's not only spam detection that we can apply Bayes classifier. We can apply it also in sentiment analysis, in topic classification. We might be able to draw more examples, in any of these areas later. It has its strengths. The bottom line now is that this naive Bayes classifier uses the principle of the Bayes theorem that I just talked about. That's why we mentioned it in any case. So that principle is what we will apply in our example for demonstration. But what are the strengths? What are the weaknesses? As you will see, it's very simple and fast because the formula is very simple, except you want to think otherwise. And then we can use it for small data, as well as for large data. Some techniques are not good with small data, but the naive Bayes works with small data, so it's an advantage. And as you will see, you can easily explain and interpret the results. Some techniques later you will also see, you can see the results, but you will not know what is going on in the process. So the Weaknesses, here we have two. The assumption is that the words are independent, that the composition of the words, are independent. But we all know that that's a very strong assumption, which is not, words are not, when you form your words or you form your sentences, they are conditional. What will come, the next word may have to will depend on the previous word. So, but this is why it is a disadvantage, because, well, it's a weakness, because the assumption appears not to be realistic. And then there is the challenge of struggling with the order of the word. We know that word order can change meaning. So the position of the word can change meaning. As a linguist, you know better than I do. So our focus here is, how do we use this approach to how do we implement the naive Bayes, for text, which is what we want to do now quickly. So to implement, we need data. We need to collect data similar to what we have here. And I'm also going to give you assignment, that you will also generate your own data similar to what we have here. I'm sure most of you have belonged to groups and you've seen different messages sent by the hackers. How many of you have received messages by hackers? Type yes. So you all, yes, Shiamaka, that's interesting. Only Shiamaka, Vivian, yeah. So who else? What of Mercy? What of Abdurrashid? What of Kendi? What of Ezegi? Final Heritage, yes. So you are going to compile in a format like this, something like this. So you are going to look at the, for maybe for the ID, that will be the first message. Make sure that you have a mix of messages, so that they don't, maybe you can have the messages that you suspect to be hackers and those that are not, that are genuine messages. So you put those messages here, just copy and paste. Then let's look at words that are, pick 2, 3. In this case, for the spam, I pick win and meeting. So you can pick 2, 3, 4 different words that you notice are frequent, and then you also label them, whether ACA message, no, or not ACA message. So you label that. So you create your own data. You can also think of other linguistic data that you can use for your demonstration, but it's not only this spam thing that you can use. You can also compile your data, look at your group messages where you are you look at you are interested in the sentiment being expressed by the members of the group. So you collect few messages. So you can look for words like congratulations, which you can consider as being positive sentiment. You can look for messages that are look for words that also indicate negative sentiment, and then you use label to now classify whether the sentiment is positive, neutral, whatever. I see a lot of that in most of our group messages, group chats. So I'm just trying to guide you how you can, build linguistic data sets for purpose of implementing naive Bayes classifier. So we have our data for this discussion, and you've seen the data. So what we have done is, if the word win is if the word win is in the message, then we assign 1, which means yes. So the original data set is something like this. The original data set is something like this. So win, is word win in the message? Yes. So is meeting there? No. Then is message spam or not spam? For 2, is win there? No. Is meeting there? Yes. What type of message? Not spam, and so on and so forth. So this is the data that we want to analyze. Our goal is to say, okay, if we now have a new data set, maybe number ID 11, and we want to use naive classifier to predict which label or which class should it be, then we will use, if our interest is to predict the class, then we will use naive classifier to now, look at, do we have win there? Do we have meeting there, as the case? And then based on the model, then and the data that we feed into the model, we will be able to predict, So the machine will be trained to say, oh, this is a spam, and then it will put it in the spam box. This is not a spam, then it will put it in the inbox. So this is what we have done. So here we simulate the data. This is the data, so to say. So we use the data frame to read the data. Remember, we have coded yes to be 1, and we have coded no to be 0. So for when anywhere you see 1, it's yes, 0, no. For meeting, 0 means the word meeting appears in the message. Sorry, does not appear in the message. The word 1 appears, implies that the word meeting appears in the message. And
It's sorry, that very heavily here, and I cannot hear anymore.
sorry, I can't hear you, Heritage.
It's raining heavily here, and so I cannot hear you anymore.
Don't worry, you will watch the video. Just follow.
Okay, sir.
Okay. So, so we will have to we will have to enter the data this way. You can also use the approach I used in the last lecture, save the data as a CSV file, and then simply use the read .csv function to read the data. So here, the data is manually entered, not that we call the data from a file. So those are two possible options you made. But this option is only good when the data point is very small, when you have just very few observations. So you can run this. So the first is to load the package that will, which is E1071. That's the package that will help you to run the naive Bayes classifier. So once you have the data loaded, then you enter the data. If you even want to see the data, you can simply type data here. So you have, this is the data that you have entered. So just the way you have it when only that the message is no longer there. We are not working with the message any longer. So this line of command helps you now to apply the naive Bayes model, and the variable label. I used a function last week. I used str function to help you understand the internal structure of the data. So this is the internal structure, which means you have 10 observations, 3 variables, and then these are the variables: when, meeting. So both of them are numeric. Label is a factor with 2 levels. So spam, no spam. So that's what to see here. So you can now use this naive Bayes function, and these are the arguments. Label will come first, followed by this syntax, which is called, this symbol called tilde. then dot here. When you put dot here, it means you are using, instead of writing when plus meeting, so I could as well just put those variables and say when plus meeting. There are only two of them, but when there are many, instead of typing all of them, we usually put dot. So dot there implies that use all the other features. So in our data, I remember last time we talked about the label and the features. So in our data set, these are the features and this is the label. So when you put dot there, it means use all the features in the data set. And this one refers to the data frame. So you can run this model, and then for you to know the result, you use the print function to be able to view the result. So this is the result, and that is what we now have to talk about. First of all, you will see here the probability, which is in this case what we call the a priori probabilities. So that reminds me of another very important concept that you might need to learn. So when we write here that this is probability of A given B, which is also probability, if I write this one first, probability of B given A, and I write times probability of A over probability of B. Now, this has a special name. We call it the posterior probability. This one, so this is posterior probability, and is the one we want to compute. When we compute it, it helps us to know whether to change our belief or to retain our belief. This one is what we call it the likelihood. This one is called the prow. The prow. This one is called the total probability. Total probability. So sometimes we write the prow. So we write the so we write the prow, so the posterior, we write the posterior to be like approximately likelihood times the prow. And then we use approximately because the total probability in this case, we have suppressed it, this total probability. Now, we won't be able to go deep into that. But if not, then we use equals to, but for now, we will be using equals to for purpose of our discussion. So the concept of prow is what you, the information that you have or the belief that you hold, outside the data. The likelihood is the information provided by the data. So in the result that we have here, you can see the a priori probabilities. The a priori probabilities. And it's simply what you get. I told you the other time, if you look at this, you have how many messages do we have? Let me ask Vivian. How many messages do we have?
10, according to the numbering, 10, sir.
There are 10 of them. That's good of you. Now, we talk about if I'm interested in the probability of spam, what would that probability be? We have 10 messages. How many of them are spam?
6, sir.
6. So what would be the probability of spam?
6/10 or 0.6.
Excellent. So that's what this one is giving you. So it's giving you the probability of spam. So you see this. Then what is the probability of not spam? How many of them are not spam?
4 messages, sir. 4 messages.
Excellent. So 4. So what is the probability of not spam? What is
40% or 0.4.
Good. So 0.4. Right? So the next set gives you the probability of the conditional probabilities. This is where you see conditional probabilities. Yeah, Vivian.
Yes, sir, I have a question. So what if in our data sets, like
Yeah.
the last one, we have both win and what's the second one? A meeting occurring in a message, right?
Okay. We've not
So
talked about that. Maybe the in the individual probability. Okay, let me hear you before I even.
yeah, so how would that affect our results? Like that's one. And then the second one would be what if, because when you showed the real message, I
Yeah.
sort of spotted some wrong annotation, right? So what if we have wrong annotation? Say in a message where there is no meeting, we are tagging it as there is meeting. And a message where there is no win, we're tagging it as there is win. And there's in the message where there is no win and meeting, we are saying that there's both win and meeting. How will this affect our results too? Or the training of the model? Because the goal
So,
is to train a model.
so those are things we want to start talking about. Those are things we start. Well, for now, the question I ask you is: you have 10 messages, and you look at the label. So from the label, you can first of all, without even looking at what win meeting, just leave that one for now. Look at the label, the variable label. So you can compute the chance that in you can compute the chance of receiving a spam message and the chance of not receiving a spam message. So the two probabilities are what we call the probabilities of each group, even without looking at the features when I'm meeting. Vivian.
Yes, sir. I understood to that point, sir. I was just thinking.
We are still coming to the one you are thinking. Let's take it piecemeal. Oh, time is not really our friend. Okay, even if I can't, if my colleagues are not able to call me, then they will have to prepare for that next class. Is anybody still having problem as to? So let me uh, show you.
Yes, sir.
Yeah. So
Oh, I understand all of this up until conditional probability.
okay.
I
So
think you have
whatever you have seen in that output, I've brought it out here for is here now. So I now be able to explain much better from here. So yeah, where are we? So this is the probability of not spam. This is the probability of spam. So from here, one could easily say that we have 60% chance of um, of having a message that is spam, 40% chance of having a message that is not spam in our data set. So now let's see the next result, which is telling about the conditional probabilities, which now takes into consideration the word when if it appears and the word meeting if it appears. Is that clear? So if the word when appears, so if an email is spam, if an email is spam, you will see here that this is when you have spam and the word when appears there, right? This is when you have not spam and the word when appears there. What does it say? It simply say for this one, if an email is spam, it always contains me, which means it always contains the word when, which means is certain. And if you look at the data, you will notice that anywhere the word when appears is always labeled as spam. So the second one, this one is saying that if it is not spam, then you have 25% chance, that the word when will appear. And then you have 50% chance that it will not appear. So even though it's not spam, you could still have the word when with this chance. 25%, and then 50% chance that it is not spam. The same thing with the word meeting. If you look at meeting, this, and you look at spam. So what this one is saying is that if the email is not spam, in this case, then it always contains the word meeting. You can see 100%. If you see the word meeting, then it's saying is sure that it is not spam. But if you see the word meeting, and if you see the word meeting there, then the chance is very low that is spam. So what this one is saying in essence is that if it's spam, there is about 70% chance it will have the word meeting. It will have the word meeting in it. And you have about 41% chance that it will not have the word, it will not have that word meeting. So this is, sorry, just a minute. So, yeah. Hello, sorry. Hello.
Yes, sir.
Okay.
Thank you, sir.
Am I back?
Yes, sir.
Yes, sir.
Okay. So what I'm saying in essence is that now we are able to give the conditional probabilities, and these are the conditional probabilities, which is as you see here is the conditional probability that if you see in the message, so you have, if an email is spam, it will always contain the word win. So this is the measure of the conditional probability. Then this is the measure of the conditional probability for not spam, given that you have win in the message. So let's run the remaining part. So to be able to make a prediction. Now we now have a new data, and in that data, when appears there, but meeting does not appear there. So we now want to predict what category will it be? Will that message be? Will it be spam or not? So line 20 gives the, the data, the new data that we have, the new email that we have. So we run that. So the machine has taken note of that, and then we can now use the predict function to now predict the category it will fall. So we can run this. So we can now call, or classify that, we use this now. First of all, this one will calculate the probability, and then this one will now help us to categorize them into class. So if we run line 20, we'll now see the predicted class, and we use the function print to print the result. So this is the result for the predicted probability. So this value is so small. This is 0.00000 about 60, which is very, very small, before you now have 48. So this is almost zero, because you have about z0 before you have 4. And then this is the probability that word that has no win in it is a spam. So which means now that you could predict the last line will now give you the particular class, which means the class is spam. So which means the classifier has classified that message to be spam. That's what that result is saying. So in summary, or in conclusion, the model that we try to develop, even though with just very simple data, look at the word win and meeting, and on that basis, the model is able to learn how to better classify message into spam or not spam. And based on the probability values that I've shown here, for instance, words like win are highly, associated with spam. And words like meeting are highly, strongly associated with not spam. So, which means the naive Bayes classifier, is able, to not only use probability, for purpose of categorizing text messages, but also gives you the measure, of that of the probability. So This is what we want to demonstrate. I know you have a bit of worry, but if you take time to digest, then you really appreciate the beauty of this this technique in natural language processing. So this is the best place to stop, but you can ask questions now to before I close the meeting. You also need to work out tutorial arrangements with Honey and Kafayat. If they,
Okay.
yes.
Okay.
So are there questions before I leave? You may not be able to do your tutorial now because I've used almost all the time. But let's hear your questions. Yes. Yes, Shiamaka.
Okay, sir. My question is this on the 13th number where you have hashtag train naive bias classifier. Like, are you the one to
We are
impute the no on the 13th number?
13th number. Here.
Yes, number. Yes,
Okay.
sir.
I
Do
told
you
you,
manually like input it?
yes, these are commands. This I told you last week that um, this anytime you see hash here, you are telling the computer or the machine that or the R that is a comment. So it's not executable. But these ones without hash are the ones that can be executed. I don't know if that answers your question.
It does, sir. Thank you, sir.
Good. So you know in this lecture you is not only to learn about the technique, you should also be able to apply the techniques. You should also know how to use the tool to be able to apply the technique. So the tool we are using is R, and you just have to get familiar with how to uh, use R codes, how to write simple codes. Even these days, you could use AI to be able to help you, to write codes. Once you know what you want to do, if you have this data, you could even use AI to guide you as to uh, the code you need to be able to run the Bayes classifier. And if you go to the lecture notes too, you have the codes. I gave you the practical code, the codes to run. So you have the step by step. First of all, you have to install the package. If you need this, but we didn't use this package in our case. We use this E1071. So then you create the data set, and I created the data set. You know, sometimes also the data set you will come from the feed or from the survey or from whatever experiment you are conducting. So you need to get the data, but the data will have, you know, uh, the features and then the labels. That's what to see. That's what to see here. So we created a data frame, and then, of course, we didn't do pre-processing, but later we will do pre-processing. Then we train the data And we use this expression also in our demonstration. Then we make predictions, and then we discuss. So those are the commands and the arguments that you need to get familiar with. So I think we have to stop here. Take time to review the lectures, except you have other very pressing questions. Sorry, Kafayat, and so maybe you should prepare to engage them fully in the next class. Any question?
Okay.
No. Yeah. So thank you very much. Take care. See you possibly next week.
Yes, sir. Thank you, sir.
You're welcome, Heritage.
So, have a great evening. Bye.